Okay, we'll begin this video by using the one-to-one property of logarithms to solve some equations. So when the equations are in a nice convenient form where we have log with the same base on both sides, then we can say that the arguments also have to be equal if the logarithms are equal. So the argument of this side has to equal the argument of that side because the one-to-one property of logarithms says that if it's log of the same base and they're equal to each other, then their arguments have to be equal to each other. And so we can say that this implies that A equals 12. Now be careful. I didn't divide both sides by log of 5, they're not being multiplied anyway in the first place. What I did was I said, if the logarithms are equal and they're of the same base, then the arguments have to be equal. Same thing here. The log is the common log in this case, so these are both log base 10. So the fact that the logs are equal implies that the arguments are equal, which means I can now use equation solving strategies in order to get 2x is equal to 3, therefore x is equal to 3/2. And for the last one, we have log base pi on both sides, and we're stating that the two logs are equal. So again, the arguments have to be equal. So by the one-to-one property, this implies that x squared minus 8 is equal to 41. And to solve this type of quadratic, it's simplest to get the square term all by itself. And then we're going to take the square root of both sides. And notice that this is going to lead us to plus or minus 7. But I want us to be careful here and make sure that both of these answers make sense once we plug them into the logarithm. They will both make sense. However, you always want to be a little careful that whatever you get for your answer doesn't cause a negative to happen inside the logarithm, because that would not be possible. So if I plug positive 7 in, then I get a positive number, so that's okay. If I plug negative 7 in, I get another positive number, so that's also okay. So just make sure you test your answers and that your answers aren't leading you to negative numbers, in which case you sort of have what's called a false solution. You can do the same thing with the previous ones, particularly part B. If you want to check it, you check and say, well, when I plug this in, I get 6 minus 3, which is positive. And when I test it here, I get 3, which is positive. And notice that they're going to be the same in all of these cases. Okay, so that's how we can use the one-to-one property of logarithms to solve equations. Now we're going to change topics and we're going to focus on graphs of logarithmic functions. The key for graphing logarithmic functions is to use the exponential function to come up with a logarithmic function, because it's much easier for our brains to think about exponents than it is for our brains to think about logarithms. So I'm going to start, if I want to graph something like y equals log base 2 of x, then I'm going to start by creating a table of values for the inverse function. The inverse function is that 2 to the x equals y. Because remember that this function is the same as 2 to the y equals x. And so the inverse of that would be 2 to the x equals y. So these two are inverses of each other. So now I'm going to fill this table of values in. I've got 2 to the negative 3 is equal to 1 over 2 to the third power, which is 1/8. 2 to the negative 2 equals 1 over 2 to the second power, which is 1/4. 2 to the negative 1 equals 1 over 2 to the first power, which is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. and 2 to the 3 is 8. So now that I have these, it's good to remember that in order to go from a table of values to the inverse functions table of values, you're simply swapping your x and y. So this is the same thing as the inverse function flipping. So we can rewrite these, and all of the ordered pairs over here came from my understanding of exponents, but lead to my graph of a logarithm. So therefore, if I want to graph the logarithm, all I need to do is plot these points. So I'm going to begin by just graphing the logarithm, but then I'm going to show you how the exponential looks like it is the inverse function. So to begin, I'm going to start at the end with 8, 3, 4, 2, 2, 1, 1, 0, and then we have 1/2, -1, 1/4, -2, and then 1/8, -3. And you can see that this is going to be getting closer and closer and closer to that y-axis. But we never will hit the 0, and we're never going to go into the negatives. So this is the graph of y equals log base 2 of x. And the way I came up with the ordered pairs for that function is by coming up with the graph or ordered pairs of 2 to the x equals y. So now in blue, I'd like to graph the exponential function so we can see the relationship between the two. So now I'm going to have -3 1/8, -2 1/4, -1 1/2, 0 1, 1 2, 2 4, and 3 8. And that leads me to this graph, which is the graph of y equals 2 to the x. Now, the idea with inverses is that you can create the inverse by reversing the x and y values of your coordinate pairs. But also remember that you can create the inverse by reflecting over the line y equals x. So if I were to put a mirror right along that red dashed line and reflect across that line, you can see how the function would create the other function's reflection and vice versa. So to summarize, if I want to create the graph of a logarithm, there's always a graph of an exponential function that you can create a table of values for. And then you create that table of values and you reverse the x and the y value, kind of like interchange the x's and y's, graph the logarithm. And it's going to look like the inverse of whatever exponential function you began with. And the follow-up question we have at the end of this page is, why don't we see negative numbers in the domain of a graph like y equals log base 2 of x? And to answer that, I think it's helpful to think of this again as the logarithmic question. So the logarithmic question is saying I'm going to take 2 to this value in order to get my x value. And the domain is all the possible x values. So this really becomes the question of what kinds of numbers can 2 to the y be? That will give me the domain of x. So we talked about this a little bit previously. If I plug in a negative 2y, if I plug in a negative value, I still get a positive non-zero number. If I plug in 0, I get a 1. And if I plug in a positive number, I get a positive non-zero value. And so therefore, the domain of this logarithmic function is automatically going to be x is greater than 0. In other words, 0 to infinity. So it can be all of these positive numbers, but we're not going to be allowed to plug in a negative number. In other words, it will not make sense to have this argument ever be a negative number or a 0.